Thank you, Shiga, Matthias, and Chris. Great stuff. Our final session before the live Q&A is what we've called Solutions in Action. And here we'll do a deep dive with two technical experts who are on the bleeding edge of battery technology. The first speaker is Matthias Trenn from the Fraunhofer ILT in Aachen, who will be talking about Excimer laser sintering of ceramic thin films for solid-state batteries. And after Matthias, I'll be back to introduce the next speaker, Pasquale Franciosa from WMG at the University of Warwick, who will be our final speaker of the day. Both Matthias and Pasquale have graciously agreed to stay for the Q&A session at the end, so please get your questions ready for them. All right, let's jump into some user stories and solutions in actions, and welcome Matthias Trenn.
Thanks, Magnus, for the kind introduction. Also from my side, good morning, dear ladies and gentlemen. My name is Matthias Trenn, and today I'm going to tell you something about the ceramic thin film sintering, mainly for solid-state batteries with an Excimer laser station. But before I go into more detail on this kind of process, let me briefly give you some background information about the company I'm working for. So I'm working for the Fraunhofer Gesellschaft, which is the leading organization for applied research with 75 institutes and 29,000 employees. They are mainly qualified scientists and engineers, and our focus on studying is on developing key technologies basically for industry and business. So we see ourselves as a link between university and industrial research. And this also applies for the Fraunhofer Institute for Laser Technology. As you can see on the bottom right, we have 3 different facilities for fundamental, applied, and industrial research. And yeah, our activities cover a wide range of areas, such as the development of laser beam sources and components, but also laser material processes like laser cutting, drilling, and additive manufacturing, and also surface structuring. This is the group where I am part of. Here to mention 3 different fields. First of all, the thin film ablation and modification, then the tailor-light structuring of surfaces for functional structures and the characterization of their properties. And last but not least, the development for processes for new energy storage systems. And yeah, for that we established a new laboratory with both equipment of either production and characterization. And one very important tool for the production is the here shown laser system from Coherent. And this laser system contains of 2 parts. The first is the laser itself, and the other is the optical guiding system, which modifies and guides the beam towards the working station. And to give you more information about this laser station, starting with the laser. The laser operates with a gas mixture of krypton and fluoride, resulting in a wavelength of 248 nanometers. That's very short, and due to that we have also very short optical and thermal penetration depths, which is very good for material processing. And due to its high pulse reducibility, shown in the top right, of 1 joule per pulse, and its maximum repetition rate of 150 Hertz, we can obtain a maximum output power of 150 watts, which is pretty large. Yeah, another unique characteristic is the optical system. First of all, to mention the top head profile with a line beam dimension of 0.5 times 155 millimeters. That's pretty huge compared to a commonly used laser system. And yeah, with its high homogeneity shown at the bottom right and its very large focus field, we can process large-scale samples, which is very good also with a vacuum or process gas chamber. Okay, now I want to tell you something about the energy storage systems for the production of which the properties of the lasers can be excellently used. Here are two to mention. On the left side, there's the structure of a solid-state battery shown. To be precise, the cathode-based solid-state battery. So the cathode is the main component and the thickest component. And on top of the cathode is a thin layer of electrolyte deposited. And there are many requirements for this layer, but there are two main requirements, which are, first of all, it should be highly lithium-ion conductive, but on the other hand, it should be electronically insulating. And the challenge in the production of these battery cells are the sintering temperatures, because the sintering temperature of the electrolyte is higher than the melting temperature of the cathode. So we have to make sure that the energy is deposited only inside the electrolyte layer when sintering it, and we have to avoid thermal damage of the cathode. On the right-hand side is a solid oxide fuel cell, which is similar in structure. Also, we have here, or this time we have an anode-based material. So here the anode is the basic layer, and on top of it also a thin electrolyte layer. As you can see, we have here less noble materials for the electrolyte, which is good because it's less expensive. But on the other hand, we have to operate the cell with higher operating temperatures. So one goal here is to reduce this operating temperatures by reducing the oxygen ion resistance. And this can be achieved if the electrolyte layer gets smaller or thinner. And maybe we can, or it would be good to maintain a grain structure. And so a sintering process here is required as well. And yeah, we did our first trial series of sintering different materials. Here we started with lithium-based ceramic. So this material can be related to the solid-state batteries. And in our first trial series, we varied the fluence, the pulse repetition rate, and the number of pulses. And here are some scanning electron microscope images shown with an increasing fluence, starting from the left with the smallest fluence, where the grain structures can be seen. In the middle, and sintering process was carried out, as we can be recognized. And on the right-hand side, with the highest fluence, not only sintering, it's a little bit hard to interpret, but we would also say that a melting process is carried out here due to a fading of the grain structure. Yeah, but sintering is possible in general, but another thing to look at is if the electrochemical properties stay the same or do they maintain. And one possibility to analyze that is looking at the crystalline structure and comparing the crystalline structure of a sintered material with the raw material. The sintered materials are here the blue graphs, and the raw material are the red lines. And we compare here two different samples with two different fluences. On the left-hand side, where a sintering process was carried out, we can see that the phase stays the same. So the position of the reflections are on the same place or at the same angles. But on the right-hand side, with the higher fluences, we can see that after the sintering processes, some of these reflections are missing. So we can say that a phase change has taken place there, and it is to be expected that the ion conductivity will be less than before. Yeah, but on the other hand, we can say with the sintering processes, a phase change can be avoided. There's only a variation of intensity which can be related to a rearrangement of the ion of the lithium ions to another lattice structure or orientation, but will not impact the electrochemical properties. Another look should be taken at the layer thickness, because with that we can determine the maximum negative penetration depth. So this is the depth beneath the material will not see any light, any energy, any thermal damage. And here you can see 3 cross sections of the same sample. And on the right-hand side, you can see that the layer thickness of the sinter material is between 4 and 6 micrometers. So that's pretty small and pretty good, thinking of the requirements mentioned before. Yeah, and with that, to sum up, we can say that the complete sintering of ceramic thin films is possible. That we have to stay beneath a fluence threshold to avoid a phase change, which can occur at higher fluences, and that we can precisely depth selective sintering these samples. Proof that the electrochemical properties maintain has to be carried out yet, but I want to mention one other thing. This process is a process which can be easily be upscaled. Thinking of a laser system that provides more power, such as the Coherent Viper system, or a larger top head profile with the line beam 1500. Last, I want to mention our new laboratory at the ILT, in which the characterization of the electrochemical properties will be carried out in the future. This laboratory is not only for the characterization, but also to present a whole process chain from the raw material to the assembled battery. And with that, I'm at the end of my presentation. Thank you very much for your attention, and I'm looking forward to get in touch with you in the future and to work together on today's technological challenges.
Thank you, Matthias. It's always great to see real-world laser applications of Excimer lasers. We really like that. So it's my pleasure to introduce the final speaker of the day, Dr. Pasquale Franciosa, who is Associate Professor and Head of Laser Welding Applications Laboratory at WMG at the University of Warwick. His topic today is laser welding in high-volume manufacturing for e-mobility. And don't forget to stay tuned and have your questions ready for the team after Pasquale's talk. Pasquale, over to you.
So thanks, Magnus, for the nice introduction, and thanks everyone for coming and listening to this presentation. So today I will talk about laser welding in high volume manufacturing for e-mobility. The agenda is as follows. I will start with a short introduction about our institution. Then I will move on the 3 core applications within the battery manufacturing ecosystem, which we have been developing using the ARM laser technology. And then I will summarize with the key facts and the future development. WMG is a stand for Warwick Manufacturing Group. We are an academic department at the University of Warwick. We are in Coventry, in UK. We are strategically located within the heart of the UK automotive hub. For example, Jaguar Land Rover is co-located on campus within the Warwick University, and we are also part of the high volume manufacturing catapult network. Our main drive, our main mission is about net zero transportation and future mobility. So clearly, energy storage and battery systems are core applications for us. Maybe just quickly, in very few sentences, I will show you also our overall research journey. So we go usually from concept readiness up to pre-production stages. So we cover pretty much all the steps from the low TRL, technology readiness level, up to medium-high TRL, TRL 7, for example, in this case. Okay, and our labs, our facilities are fully capable of upscaling the manufacturing and the joining process from the concept feasibility stage up to the pre-production stage, as you can see here within the slide. Now, talking about the applications we have been developing using the ARM laser technologies, you can see here three examples. So clearly, given the time, I am not discussing all the applications we have developed, but I have only selected some, let's say, the 3 core most relevant one for today. So let's start from the equipment. First, we have used the Coherent 10 kilowatts ARM laser 10 kilowatts integrated with the Precitech Weldmaster, and then also interesting to mention the sensor we have used for in-process monitoring of the weld depth penetration, the OCT sensor from Precitech, the IDM sensor from Precitech. So the first application is cylindrical cell assembly. We are dealing with the tin foil and the similar material. More details, by the way, can be found within the paper you see here on the bottom of the slide. So this application has been driven by the fact that when we are in the, let's say, full-scale manufacturing system, we are dealing with manufacturing tolerances. And given the thicknesses of those components, any variation in either dimensional or geometrical can have significant impact on the weld penetration. So the idea was to combine the OCT sensor with the ARM laser technology to achieve, first of all, stable process, and this is mostly driven by the ARM laser. And because of the stable process, we also aimed to have increased accuracy in the process and reduced, let's say, variation in the measurement. So on the slide, you can see now the conceptual configuration. Just one comment is about the twin-tech technology we have used for the OCT sensor. So again, we have used a dual beam, not only for the welding process, but also for the sensing process for the OCT. So the first beam was pointing towards the bottom of the keyhole, and the second beam was pointing towards the top of the aluminum that is actually here. That means it's the top part. So let's see how we have developed now this application. So we tested the impact of core only or core plus ring. Okay, so the process window now is shown here within the slide. So we selected the power level in such a way we had very similar penetration for both ID1 core plus ring and ID2 core only. So this corresponds to basically the position B here within the slide, and you can see also the cross section. This is what we call now sound weld. Okay, so this was our baseline as a reference. Okay, so having this in mind, then we also took some high-speed video with the high-speed camera. And this now, if you only focus at, let's say, the video on the left-hand side and the video in the middle, the video on the left-hand side is the one corresponding to core only. The one in the middle is a core plus ring, and we can see clearly that when we use core plus ring, there is is a more smooth process with a reduction in sputters. And because sputters is most probably related to the instability of the molten pool and instability of the keyhole, we aimed to understand if this is true and if this is reflected within the OCT signal. This is what we have done now and what I'm showing within the slide. So if you really look, and if you consider now, you have this ID1 twin-tech on and ID2 twin-tech on. So the first two box plot on the right-hand side chart, what the result is telling us that the average weld depth error is quite significantly reduced in case of ID1. ID1 again is the case with the core plus ring together. And the error we are plotting is the error between the measurement of the OCT and the measurement we take directly with the destructive cross-section. So there is almost 50% reduction in error by using this core plus ring. So the benefits are quite clear in this application, saying that because the welding process, in case of properly selecting the laser power on the ring, the welding process becomes more stable. Because of that, also the measurement with OCT is more repeatable, and the error is also significantly reduced, as you can see again from the result on the slide. The second application is more related to the casing and enclosure assembly, specifically looking at construction with the high-intense aluminum 6000 series. More again details can be found within the paper which I have cited on the bottom of the slide. So the overall challenge was to say, yeah, okay, interesting. We know that 6000 can be welded with the filler wire, and then we can get rid of cracks and micro cracks problem. But question is how, or is there an alternative to that? So can we use the ARM technology, so dual beam shaping technology, to achieve very similar results? And this is what we did actually. So we have compared few different configurations: setup 1, 2, 3, and 4. Setup 1 was beam oscillation and power modulation. Setup 2 was the as setup 1 but with the core plus ring laser. 3 and 4 was mostly with the filler wire. So now, if we look at the result of the lap shear, yeah, so the linear lap shear, we see, as expected, that in case of using the filler wire, the strength of the joint is significantly higher, 50% almost compared to setup 1. However, we also notice some significant improvement between setup 1 and setup 2. So it means the integration of the beam shaping core plus ring has improvement in terms of reduction of number of micro cracks within the weld. The last application I will show now is let's say on very opposite side of the tinfoil. So now we are talking about structural components, and specifically cast to extrusion application. So we have thick components, nearly 2 millimeter or above. And again, more details can be found within the paper which I have cited on the bottom for your reference. The main challenge in this application is mostly about the porosity formation, which is a consequence of the entrapment of hydrogen within the base material, within the cast material during the casting process. So question is how to get rid of this porosity of this gas during the welding process. And this is interesting because after conducting a very comprehensive study with several parameters such as the power on the ring, power on the core, scanning frequency, scanning width, and focal offset, what we have realized that the joint effect between the power on the ring and the scanning frequency, this effect is the predominant effect for the reduction in the porosity, as you can see now from the cross sections. So the top one is probably one of the most optimized with the minimum level of porosity. The bottom one is the, let's say, the unoptimized one, where we have significant porosity within the weld. So really, in combination of scanning frequency and ring power has beneficial effect on the weld quality overall. So now, if I can conclude where we stand at this moment, so I have shown three applications. The first one was a tinfoil dissimilar material. The main objective was, well, we had two sub-objectives for this application. So the first one was proving that using ARM laser technology we can achieve a stable process, and indeed we have seen a good result on that. But even more interesting is saying, okay, even though we have a stable process, is it possible to achieve a repeatable and accurate measurement using in-process sensors such as OCT? And this also was, we achieved some promising results. The data has shown an improvement of 50% in terms of accuracy when we use the dual beam, so core plus ring, compared to the case of only core laser. The second application was about the welding of aluminum 6000 series. The challenge is about controlling the crack level, either macro crack or micro crack. Okay, without filler wire. This also, I want to stress again that we didn't use any filler wire for those experiments. And the result also confirmed that there is a like 10 to 15% improvement of the joint strength if you use if you optimize properly the power level on the ring. Okay. The last application was about cast to extrusion, where the challenge was about the control of the porosity. And what we have concluded is by controlling the joint effect between the scanning frequency, so we are talking about using a wobbling head or oscillating laser beam. So by controlling the joint effect between the scanning frequency and the ring power, we achieved almost zero porosity within the molten pool, let's say within the weld. So all in all, the real future probably improvement and the future development that we see now out of these three applications is really within the 6000 series aluminum, where even though we have some improvement within the weld in terms of strength and therefore reduction in terms of cracking level, however, more investigation is required to increase the strength even more and make it, more compatible with expected stress of strength level within the weld. Thanks for your attention. I have left all the details on the slide, so you can either contact by email or also you can ask questions during the Q&A session, which I will be attending anyway. So thanks.
Thank you, Pasquale. That was great. So at this point, we're ready to start the Q&A session. So get your questions ready, and I'll hand the word over to Mark. Mark, please go ahead with the Q&A session. Thank you.
Excellent. Thank you very much for the introduction, Magnus. So we're now entering the question and answer period where we have our team and experts standing by. So first of all, I'd like to thank everyone for listening to us and posing a bunch of great questions. We'll do our best to get to them, but if we can't get to them, we will be able to follow up individually with them. So I will start. So again, I'm Mark Auger. I'll be moderating this question and answer period. So we got lots of great questions. So I'll start off. There's a couple questions about fiber diameters. So we actually have 5 fiber diameters in the ARM laser, ranging from a 22 micron core up to 100 micron core, and a ring size from 140 to 290. 2 of those are available in fiber-to-fiber couplers, so a disconnectable fiber as well as a switch. There's lots of data sheets on our website. Additionally, you'll be able to rewatch this video at any time on our website. There will be no formal presentations, but please watch it. So with that, move on to our first and most popular question, which I'll direct towards Peter Klaga about how the welding depths of laser changes the material properties.
Okay, Mark, thank you. Yeah, good question. So changing material properties is always a problem, especially for the copper materials. And yeah, the heat affected zone is normally reducing the electrical conductivity of the copper. And for that reason, customers ask us to achieve maybe 120% of the material thickness as a connection width. That's true for hairpin welding, but also overlap welds of different sheets, for example.
Excellent. Thank you very much, Peter. Sticking with you, we got a couple questions about some different thicknesses of material, especially copper and aluminum. I know you had a great slide about that. Do you want to provide some insight?
Yeah, sure. The maximum thickness, it's not really possible to define. It's always a question of how much aluminum you get into the molten copper, or the other way around. Then you will end up with some brittle faces, and that's the problem. What we have done already in the lab is welding copper to copper, going through a 4mm thick sheet and end with the root of the weld in a 1mm thick sheet. So there was not a full penetration. That's quite good to control, but it's not really comparable with the situation with the dissimilar joint between copper and aluminum. There we always try to stop when the copper is on top. In the aluminum, maybe 0.5 millimeter, something like that. But that's really depending on the material thicknesses we have and we have to weld.
Excellent. The next one that I have is about bus bar welding, where we talk about spatter reduction. So if you can provide a bit more comment on what we mean by reduction and what we see is left.
Spatters are reduced almost to zero. So I guess you have seen the high-speed videos in the slides, and there weren't any spatters really leaving the welding process, especially where we welded this circle and the sinus curve. So we're really down to a minimum of spatters, and what is left as spatters is more comparable with some sort of dust. So you will not end up with big balls of spatters bouncing around on the clamping on the part and burning into surfaces, for example. That will not appear using the ARM laser.
Okay, great. Thank you very much. The next one I've got on my list is talking about the power differences between core and ring. So actually, I think I kind of want to tie this one. So if you can comment on what combinations we have available, but there was also another question just with regards to the total power with the ARM laser when using a ring and core versus a standard. So if you can kind of combine those two, that'd be great.
Yeah, I mean the ARM lasers are available up to 10 kilowatts, and as the lasers are made of up to 4 modules, we can combine them as we like. So we can add 1 module to the core and 3 to the ring, or the other way around, or 2 in both components. For the most copper applications, I would say a 50-50 ratio between the core and the ring power would be really suitable for the application.
Okay. And then with regards to the comparison of total power when using an ARM laser versus a standard, how would you say that?
Yeah, the advantage of tailoring the intensity of the beam, we have the possibility to shape the keyhole as we need it, and due to the different angle of the keyhole walls, we can increase the number of reflections inside the keyhole, and with each reflection, you get the laser power into the material, and depending on the power ratio, we can really achieve a very high process efficiency, even higher than using a standard top hat, for example, fiber or a spot for welding applications.
Excellent. Now I'd like to move on to Pasquale at WMG. We got a question with regards to the shielding gases you were using and your aluminum and some of your welds.
Yeah, okay, thanks. This is a very good question. We didn't use any shielding gas at all, because the idea was to implement a fully remote laser welding process. So clearly we can use shielding gas, argon, for example, but if we can avoid, we prefer to avoid, because having the shielding gas in the full-scale production has, there is a clear cost implication for the consumable, and also brings additional complexity to the system. So the project we are running at this moment is the expectation is not to use shielding gas if possible. And I guess using the capability of the ARM laser, we are going in the right direction.
Excellent. Next question, I'll stick with you, is about were you not able to eliminate hot cracking in 6000 series, or did you just reduce it?
Okay, so I think elimination of hot cracking is still something ongoing. So this is a question of 1 billion pounds, probably. But yes, so reduction we had a clear reduction of the hot cracking. Definitely the central line crack was eliminated. What is still remaining are the micro crack, so transversal micro cracks, they are still remaining. But we have noticed significant, let's say, decent, good improvement compared to the single beam welding. So we see somehow the way forward using the dual beam technology, which is helping in preheating the material and reducing the thermal gradient. So there is good room for, for further improvement. But I think this is the right way forward. If we don't use filler wire again, because with filler wire, obviously things are different. So we are talking with no filler wire.
Okay, great. And then the last set of questions, just sticking with you, we have 2 questions just with regards to quality control and sensors. So between Industry 4.0 and sensor fusion. So if you can give us your thoughts and insights on that.
Yeah, okay, so thanks for this. So yeah, so I mean, in the end, I mean, the quality, the development of the process parameter is probably 50% of the full picture. So do that anyway. But then when we end up in the full scale production, clearly there are variations. So manufacturing tolerances and so on. So sensors are important. We have been exploring different sensing solutions. So the OCT is one of those. There are clear other options like diodes or even acoustic emissions. So these things are also possible. The real question probably is to say, okay, we can integrate sensors together. This is possible already. So the next step is to how to get use of those data in an intelligent way. So what we feel is that using like machine learning, artificial intelligence, these new tools appearing more and more in the productions, in the manufacturing systems, I think is going to be the future. So more and more integration of software and data science within the this welding engineering community. So this is probably what is going to happen as in the next few years.
Excellent. Thank you very much. So moving on now with our other guest, Matthias from ILT Fraunhofer. So we've got a couple questions about your work. So one of them has to do with using a pulsed laser versus a continuous laser.
Pulsed lasers are here better, especially in the nanosecond range, for the precise deposition of the energy. Continuous laser hasn't too deep optical and thermal penetration depth. So nanoseconds lasers give us the opportunity to more precisely deposit the energy.
Excellent. And then the next one is what are the advantages of using Excimer lasers for sintering over femtosecond or solid state, I think, UV solid state lasers?
Okay. There are mainly 2 advantages. First of all is the very small wavelength. As I mentioned before in my presentation, there are requirements for a small optical and thermal penetration depth. So we can precisely deposit our energy within the first, let's say, 5 to 10 microns. So wavelength is the one thing. The other thing is comparing the pulse lengths. Femtosecond laser pulses are shorter, and with that we gain an ablation process, but here we want to have a sintering process or a melting process, and with the longer pulses we can achieve that. So these are 2 great advantages compared to solid state and femtoseconds lasers.
Excellent. Thank you very much. And then the last one I've got for you is, how is the daily living with an excimer laser with regards to gases and optics?
We can't complain. So for us, it's very, very good. Yeah, we have to refill the gas every 2 or 3rd week. But yeah, we are a research institute, so we don't run our lasers 24/7. But the Excimer laser, especially the LEAP laser, is a very good laser system which runs every time. Let's say we have our laser systems which give us more problems, but it does its work every time.
Excellent. Thank you very much. We still have a little bit of time, so I will jump back to Peter. So the next question I got on my list is, if you can comment about surface prep via laser cleaning or other methods prior to welding, and what you think with regards to strength or anything else.
Yeah, I mean, there are two topics. One is a coating that has a function, and then you have contaminations. Contaminations are always bad for welds. So some oil from a deep drawing process or something like that, that definitely will be a negative influence to the welding quality. When we now talk about surface coatings which have a function, anti-corrosion, for example, or something like that. Then it depends on the alloy. So zinc-coated steel sheets, for example, the zinc is not that big problem for us. It can cause pores, but with the ARM technology, we can even weld zinc-coated material without a gap in between. And when we are talking about aluminum silicon-coated material, so hot pressed steel, for example, there the aluminum can do some harm to the weld and reduce the mechanical strength. But then it's really depending on the welding parameters you're choosing, where the aluminum is going, whether it is removed before the welding process, for example, by another laser type, pulse laser, for example, or you choose the joint geometry or the welding parameters the way that the aluminum is not alloyed too much into the weld seam, or it doesn't create too big brittle faces, for example.
Okay, great. I got one more for you before I move back on to Pasquale. Have we seen that the ARM laser technology has been able to eliminate or replace wobbling with a standard fiber laser?
Yes. So the principal idea of the core ring constellation for the fiber is that we try to avoid the wobbling, as it is reducing typically the process speed. You have an additional movement of the beam, and we can avoid that by the right ratio between the core and the ring. So we can use the still standing beam and use the full laser power to generate process speed, for example. So that's a real benefit of the core ring design.
Great. So moving back, so for Pasquale, got a question about the accuracy of the OCT sensor when you're looking at thinner, low thickness material.
Yeah, okay, good question. And probably this was our motivation, even initiate this work in the first place. The accuracy of the sensor, well, is probably independent from the material. So the sensor is definitely accurate. The inaccuracy comes because of the process, and well, especially for the thin foil, dissimilar materials. So what we have noted, yeah, so that we have achieved something in the range of 0.1, so 100 microns error compared to the data from the macro sections from the metallographic analysis. The spread in the data was also somehow acceptable, so it was below 50 microns. And we have noticed significant improvements while using the ARM laser. So with ARM laser, we had a very clean, let's say, key welding process with stable keyhole, and this helps quite a lot in improving the measurement accuracy. with the OCT.
Okay. And then I've got time for one last, so I'll stick with you. So there's a question about, do we still see the need for optical inspection to guarantee 100% quality? So with the work you've been doing with the ARM laser showing a more stable process as well as some of these sensors, can you provide your thoughts on whether or not it can be eliminated or reduced in production?
Yeah, I think, in the end is always the pushing from two ends. So pushing from the process and pushing from the quality and from the sensor perspective. So yes, so we see significant improvement. I don't think I can state we can get rid of all the sensors right now, but yeah, there is improvement. So I think if we keep working in this direction, at some point the need for inspection might be reduced. Eliminating completely the inspection, well, it's also a business decision, because I mean, in the end, it's also a business decision. So this is not easy to give a straight, complete answer, but yeah, things are evolving in that direction.
All right, so I just want to thank all of our guests for participating in our question and answer. It was very good to have you here, so appreciate the presentation and appreciate you sticking around to answer the questions. I'm sorry we didn't have time to get to all the questions. It shows how great the talk was that we generated this many questions. So again, thank you to Peter, Matthias, and Pasquale for participating, and thank you everyone for attending. And with that, I'll hand it back to Magnus for his closing remarks.
Well, that was terrific. Thank you to all of our speakers and panel members, as well as all of you who attended today's sessions. I hope you found it informative and instructive, as I did. All of today's presentations, if you missed anything, all of them will be posted right here on the Coherent website, so you'll be able to look at events again. We'll also have an email survey as a follow-up, so we'd very much appreciate to get your feedback on what you liked, what you didn't like, how we can do it better. And we hope to see you back for future Coherent Amplify events. Thank you again for attending.